Hi, I'm Jack, joined by Amber and Carlos, and we're going to be discussing the fabrication methods and applications of carbon nanotubes. There are three main fabrication methods, these being listed here: electric arc discharge, laser vaporization, and chemical vapor deposition. We're going to be focusing primarily on these, but please be aware that there's a number of others, most widespread being ball milling, electrolysis, pyrolysis, polymer heat treatment, and partial combustion. But since we're going to be focusing mainly on these three most popular methods, we've organized this presentation into three parts, each focusing on one fabrication method and then a major application of carbon nanotubes. Alright, so the first method of producing carbon nanotubes that we're going to discuss is the electric arc discharge method. The advantage of this approach is that it can produce large quantities of carbon nanotubes relatively quickly, and with the use of the right catalysts, it can produce single-walled carbon nanotubes. But unfortunately, it tends to produce essentially a large mass of poorly differentiated carbon products. The nanotubes are only one of them, and as a result, you have fairly poor control over the property of the nanotubes created, and some subsequent purification is required to isolate just nanotubes. And additionally, some of the reagents required are somewhat expensive, so it's not the cheapest and most economical approach. Essentially, the way the electric arc discharge method works is that two carbon electrodes, an anode and a cathode, are placed together in an inert environment, and an electric arc is struck between them. The result is that carbon gets eroded off of the anode and, in theory, deposited on the cathode, although in practice it's generally deposited all over the reaction chamber. The carbon produced is generally a mass of soot with a variety of kinds of carbon nanoparticles, including graphene flakes and carbon nanotubes. Now, because it's relatively undifferentiated, we don't have very good control over the properties of the nanotubes produced. And additionally, if you want just carbon nanotubes, subsequent purification has to be used in order to get rid of everything else. But with the use of some catalysts and control of the process gases, as well as some of the parameters with respect to the electrode diameter and separation and voltage, some degree of control over the nanotubes formed can be achieved. However, this is still limited even in the best of cases. So the result of this arc discharge process is a soot that coats the entire chamber, and that soot contains a number of compounds, nanotubes among them, but also a large quantity of graphene flakes and other undesirable carbon products, which is why we call it soot. So in order to get pure nanotubes, some purification is required, and there are a variety of methods available, including boiling the soot in acid, microfiltration, chromatography, usually in combination with more filtration, and thermal oxidation of the impurities, essentially burning off anything that isn't nanotubes. But all of these methods tend to reduce the total amount of product. They damage the nanotubes themselves and can destroy some of them, so usually they have an efficiency of about 5%. So the vast majority of the nanotubes originally produced by the electric arc discharge are destroyed by the purification. So that brings me to our first application, which is tissue engineering. A tissue is any large mass of differentiated cells that forms a function in the body, and the objective of tissue engineering is essentially to artificially grow these. There's a number of applications for tissue engineering that are anticipated. These include growing replacement organs that will perfectly match the recipient, improvements in healing from injuries and surgery. There's potential life extension applications, as well as relatively mundane things like just growing lab-grown meat. However, in order to do that, we have to actually be able to grow large quantities of cells and control how they differentiate and the microstructure of the tissue. And this is the domain of tissue engineering. One of the critical challenges in tissue engineering is controlling the environment that the cells grow in, because cells have a great deal of sensitivity to the parameters of the environment they grow in, including the chemistry, the amount of stress and strain around them, flow characteristics of any fluids they're exposed to. They can even be sensitive to electrical fields that they're growing under. So the design and control of extracellular matrices, which are in this particular case, artificial extracellular matrices that are designed to sort of replicate the function of the body's own natural extracellular matrix, uh, are an active area of research, and carbon nanotubes have a number of potential applications within that field. The primary value of carbon nanotubes in functional extracellular matrices is their strength and flexibility. But they also have the advantage of being functionalizable and good at cell adhesion. Essentially, what this means is that the chemical properties of carbon are easy for a cell to bind to, mainly because the carbon nanotubes on their own tend to be hydrophobic, and hydrophobic domains on the cell and on the carbon nanotube are held together in a biological environment. But additionally, carbon easily bonds to carbon-based hormones and growth factors, which affect the growth of cells and can be used to promote their replication, which is important in turning a few cells into a large quantity of cells, and can be used to differentiate them in order to create the desired tissue. Additionally, when used in semi-liquid or gel-type extracellular matrices, they affect the viscosity, and they always affect the conductivity because carbon nanotubes, as will be discussed a little more later, have a number of interesting electrical properties, but they are generally conductive. So the bottom line is that carbon nanotubes, when added to an extracellular matrix, improve the strength, the flexibility, and the viscosity of that extracellular matrix. They promote cell adhesion. They can be used to promote growth and differentiation of the cells. And although I didn't dwell on it, there's a potential there to also turn the ECM into a sensor that can provide us with information on the activity of cells at an individual cellular level. However, there is one major drawback to carbon nanotubes as an extracellular matrix additive, which is that they are not biodegradable, and if not functionalized, very short lengths of carbon nanotubes can be toxic and can kill the cells in the matrix. So some degree of processing is required in order to mitigate that aspect.
One another method for fabrication of carbon nanotubes is known as laser vaporization method. In 1995, Smalley et al. Introduced this method. This method has a lot of advantages, like it allows great control on growth conditions. It also allow continuous operation, and carbon nanotubes produced by this method has better quality and can produce higher yield as compared to arc discharge method, where we can only mostly produce single wall carbon nanotubes. In this method we can produce both multi-wall and single wall carbon nanotubes. Some of the disadvantages for this technique are, this one is really expensive technique since we are using lasers, so it's energy expensive method, and for synthesis process we need metal target, metal carbon graphite target. But Smalley et al. Use this experimental technique for fabrication. They used only laser vaporization apparatus. Laser beam is focused to a 6 to 7 millimeter diameter spot onto a metal graphite composite target. Carbon target normally contains 1.2% of cobalt nickel with 98.8% of graphite composite. Then flow tube is mounted into the higher temperature at almost 1200 degrees Celsius and under 500 torr argon pressure. Then if the from here you can see this oven is used for temperature control. Then a black powdery substance moved from high temperature zone to water cooled copper collector positioned downstream just outside the furnace. Then the nanotubes will get together from soot and stick with the walls of the flow tube. Carbon nanotubes produced by this method are purer, almost 99% purer than carbon nanotubes produced by arc discharge method, and those have very narrow diameter, about 1 to 1.6 nanometer for single wall carbon nanotubes. Also, there are some quality and quantity factors that affect fabrication of carbon nanotubes. First is amount and type of catalyst. Amount and type of catalyst affects carbon nanotube synthesis. We can get carbon nanotubes with different diameters by changing catalyst amount and type. Then the laser intensity is also really important. The laser intensity corresponds to optimal heating of target surface that increase the growth of carbon nanotubes and their arrangement in large bundles. The type of produced carbon nanotubes is highly affected by the applied pressure and temperature of the carrier of inert gas. Increasing the temperature increase cooling rate, and then less carbon nanotubes are produced. Also, the inert gas matters. Normally, we use argon and hydrogen gas as a carrier for laser process, but lighter gases are more efficient for rapid cooling than heavier ones. Also, the fluid dynamics of all the process also matters for quality and quantity factors. There are some thermal properties of carbon nanotubes. Carbon nanotubes have high thermal conductivity, that is approximately equal to 2,800 to 6,000 W per mK for single nanotube at room temperature. The stiffness of the carbon bonds helps to transmit vibration throughout the nanotube that provide a very good thermal conductivity. The second thermal property of carbon nanotubes is related with specific heat calculations. Specific heat calculations of carbon nanotubes is different from 2D graphene and 3D graphite, but it shows direct evidence of one-dimensional quantization of phonon band structure, and specific heat only shows weak effects of coupling. Then low temperature specific heat gives information about dimensions of the system and also about the phonon dispersion. In this way, carbon nanotubes have low coefficient of thermal expansion. There are many biomedical applications related with laser vaporization and thermal properties of carbon nanotubes. Carbon nanotubes are widely used in imaging and cancer photothermal therapy. Carbon nanotubes photothermal therapy has a lot of advantages, like it's non-invasive, harmless, and efficient technique for killing cancer cells. In this, I'm going to discuss infrared photothermal radiometry, that is a useful tool for controlling temperature dynamics in cancer cells with carbon nanotubes. In this process, carbon nanotubes can absorb near infrared radiation and then convert that to heat. Since we are using laser for this for the photothermal therapy, that gives us great tumor targetability. We can insert a sample directly to the tumor cells that can less harmful to the healthy tissues. This technique is mostly studies in vitro studies, but we can read some papers about in vivo model, but this one is really interesting technique, but we still need further investigations by in vivo and real life models.
Hello, I'm going to explain the vapor deposition method, which is a method becoming really popular in recent years due to the potential scale-up possibilities. This method consists in the pyrolysis of hydrocarbon source such as acetylene mixed with a noble gas such as argon that produce an inert atmosphere. And this mix is preheated at 180 degrees and then passed to the furnace zone where it's heated up. And in this zone, it dissociates the carbon and the hydrogen, and the carbon precipitates over the surface of a substrate that could have a metal catalyst nanoparticle where the carbon nanotube is formed. These leave remaining gases that are recovered into exhaust zone container. During this process, there are two growth mechanisms. We have the tip growth and the bottom growth. The difference between these two are basically that during the dissociation phase, in the tip growth, the particle detach from the surface of the substrate, generating the growth of the carbon nanotube from the substrate and the bottom part of the nanoparticle. That in the other side, we have that the bottom growth, the carbon nanotube precipitate in the surface of the nanoparticle, growing a carbon nanotube in the surface of this nanoparticle. The resulting carbon nanotubes could have different forms with respect to their surface structure and their form. The surface structure could be a armchair structure, which is this form where the hexagonal form are located side by side along the carbon nanotube axis. We have the chiral surface structure that is hexagonal, that are make a spiral along the surface of the carbon nanotube, and we have the zigzag that are basically when the zigzag structure form along this axis of the carbon nanotube. We could also have a single-walled carbon nanotube or multi-walled carbon nanotube that are formed in this range of temperature in the chemical vapor deposition. Due to their outstanding electrical properties, armchair carbon nanotubes have metallic properties. And in theory, these metallic nanostructures can carry a current 1,000 times greater than metals such as copper. Another interesting property is that chiral carbon nanotubes exhibit a semiconductor behavior with a really small band gap characteristic. We also have that there are many biomedical applications. In this case, due to their outstanding electrical properties, carbon nanotubes are widely used as a biosensor because his possibility to bioconjugate the carbon nanotube surface with a wide variety of organic compounds. And for this reason, carbon nanotubes could be used to develop an electrochemical biosensor capable of sense a wide variety of biomolecules that could use to detect pathogens in food or water and detect DNA copies or unspecific nucleic acid, or it could also detect infectious agents such as disease markers that detect certain kinds of disease. In this case, the electrochemical carbon nanotube application in a biosensor are electrochemical carbon nanotube biosensor that are basically a modified electrode using carbon nanotubes. As a result, we can obtain electrocatalytic activity towards the oxidation of determinate type of biomolecule. For example, Xu et al. Develops a electrochemical biosensor that modified the electrolytes with carbon nanotubes to detect the concentration of ascorbic acid in a solution. As we can see in the top image, we have a linear dependence over the time of the current, changing the ascorbic acid concentration. And we can also have this detection in a mix of several solutions, as we can see in this image, that the addition of other compounds to the solution didn't have a significant interference to the sensing of the ascorbic acid into the solution. So we can see A to F, the addition of different substances to the solution that didn't have a significant response from the electrochemical biosensor. But if we add ascorbic acid, it will have a significant response from the electrochemical biosensor. This is one of the examples of the biomedical application of these carbon nanotubes. I think it's all for our part in this case. So we have the reference where we base our work. I hope this presentation were helpful for you. And if you have further questions, please let us know, and we will be happy to answer all your questions. Thank you for your attention.